see you. All right. I just want to comment on that before I do all the intro stuff. I mean, you let one BattleBot that's like 340 pounds go into a crowd of people, and I swear, he will never let you live it down. And by the way, Jackson, who's here somewhere, right here, Jackson, stand up. He volunteered to be tased by the taser drone. Although he was an intern, so I don't know how voluntary that might have been. All right, so we've got a lot to cover today. And I am not a physicist. I'm not Brian Greene. I'm not Neil deGrasse Tyson. But I'm fascinated with quantum computing. And I'm going to do the best I can to try to get you to be fascinated with it, too. It's a very complicated topic. I was able to reduce the number of math slides to 10, and the total number of slides to about 110. So we're going to rocket through stuff, and we're going to try to leave some time for some Q&A at the beginning. So with that, the only other thing I need to say on the intro is this is IEEE Tech for Humanity series keynote. I am a senior member at the IEEE. For those of you who don't know, it's about a 480,000 organization member of electronic and electronics engineers. And they have a bunch of stuff going on here. They have a booth in the trade show you should check out. They have a bunch of other speakers. You can look for this graphic, not the snake graphic I built, the other graphic. This is IEEE Humanity series to find out about some of those. So let's dive right in. I am on a mission to humanize quantum computing. This is an incredibly complex topic that when I first got interested in it, I was like, this is great. It'll be like everything else I've done. And like next week I'll be an expert. And it's been a couple years, and I'm not even remotely an expert. And I think what gives me comfort is a lot of the other people that are my constituents in the field, they aren't either. This is very, very cutting edge stuff. It's super, super cool. And there's a lot of confusing around it. But humanizing quantum is the goal, and hopefully we'll do that today. That said, how are we going to do that? Well, I'm going to give you an elevator pitch for what quantum computing works. I'm going to tell you who's interested in this technology, where are they located globally, who's investing in it, what's going on in the startup scene and the universities and stuff. I'm going to give you a brief history of quantum computing. When did it become a thing? Because when you hear quantum computing, if you go Google it, everybody says, oh, in the 80s, Feynman did this. But it actually goes way, way back. I mean, all the way back. Think about Ada Lovelace in 1830 and build off of quantum information systems and computer science and information systems, for quite some long time. So we're kind of at an inflection point, I believe, right now. Then we're going to say, what is a quantum computer? How do these things work? I'm going to give you some, hopefully, real-world good examples. And then I'm going to tell you why we need them. And then the last thing is I'm going to ask each and every one of you to get involved somehow, because I believe that quantum computing is another paradigm shift in computing. And I think it can change what we think of as computing more in the next 10 to 15 years than computing has evolved in the last 100 years. So let's kick it off. First thing we want to cover is all the conspiracy theories. When you read an article in any of the tech rags about quantum computing, bits are dead, quantum computing's it's gonna kill encryption, and things are over, and no more blockchain or Bitcoin or whatever. I tend to lean on the more positive side of this. I tend to think that there'll be quantum encryption and better things. But these computers are not supreme to classical computers. You cannot operate a quantum computer without having a classical computer help you manage the environment, the temperature, and the data, et cetera, et cetera. So think of this less as of a replacement for classical computing and more as an extension of its power. So let's talk about who's interested in this. There was a great article by Jason Palmer in The Economist that pulled a lot of data. And what he found was that all of these countries have been investing hundreds of millions, billions of dollars over the past 10 to 15 years in quantum computing. Now, what's ironic is you'll see those big dots over the US. We're investing a fair amount, but we're not necessarily, depending on who you talk to, leading. And so if you're a nation state, you tie into that bits are dead thing, and you start thinking, oh man, somebody's gonna have a quantum computer, they're gonna break our encryption, and then that's the new weapon, right? And so this concept, this weaponizing of quantum computer, I think is ridiculous. But that's what's driving a lot of the investment from these governments. That and quantum information, where you can use entanglement to basically build new networks and new communication networks. But when you look at the patents, the United States was leading in 2015 with 295. Now, why are the patents interesting to quantum computing, what we're talking about? They're interesting because this is a measure, as you'll see here in the next slide, of the inflection point that we're at. Look at 2014. Look at all the way back to 1998, and then look at between 2014 and 2017. Every single sign that you can find points to more and more interest, more and more resources coming to quantum computing. If you look across, qubit-related patents, hardware, and applications, they're all trending up. This is an incredibly important moment in the history of computing because these and other indicators show us the inflection point. And I believe when more people get involved, I believe when there's more open source, when there's more accessibility to this technology, then that's when a technology really takes off. And I think we're going to be seeing all of that in the next 2 or 3 years. So back to those nation states. They're all worried that it's a big spy game and you're going to break the encryption. But the irony is if you look at the patents, there's all kind of entanglement with people from all over the world that are research scientists co-authoring these patents. So there's not one nation that has one quantum group of research scientists that is going to destroy everything. We're all working together on this anyway. And I hope that that becomes a realization with those groups, and I hope that we continue to build off of that. So universities that are working on it, I only picked a few. There are a lot more. I want to call out University of Waterloo, who's done a lot of groundbreaking work. My friend, Professor Nishimori at the Tokyo Institute of Technology, basically was one of 2 people who invented quantum annealing, which is one of the computers we'll talk about. MIT and Yale have been doing some great work, as has Berkeley. And then finally, the University of Texas here in Austin actually started a program to teach quantum computing at the school. It's not the only one, but it's been very well thought through. And Texas A&M has a guy named Helmut Katzgraber, who is phenomenally smart, who has also been working on quantum computing there. So there's a lot of work coming, and you're starting to see now more courseware, hopefully more open courseware, and more involvement from these universities directly in this technology. Company-wise, D-Wave may be a company you're familiar with. They're about 16 years old. They make what's called a quantum annealer. They are the first commercially available quantum computer. But Google, Microsoft, IBM, and Intel have been making tremendous progress. We'll look at that in a second in the history. And then startups. I have a bunch of friends here. I particularly want to call out Will Zing from Rigetti, who I love, and my absolute #1 favorite person in quantum, Andrew Fersman from 1QBit. They are 2 great actors in the community, and there's a lot of them, Jerry Chow at IBM and everything, but when you see these startups, it's in quantum not like other startups. I'm not hiding the secrets from the other startups. I'm not seeing them as competitors. This is so complex and so world-changing. We're all working together, and it's like one big family, and that is super exciting, and I really love that aspect of it. Now, everybody has to have one slide to upset everyone in the room, right? This is that slide. All right, so artificial intelligence, we all know Elon Musk is petrified. I think that was clear the other day. But I don't think he needs to be just yet, because even though there are people, psychologists, physicists, a bunch of people that argue each side of this argument, nature is quantum mechanical. And personally, I believe that means our brains are more quantum mechanical than they are classical systems. So if you are going to create an artificial intelligence, I think you're limited on whether you can do that in a classical system or not. So I don't think we get to a true AI until you have a classical quantum system working in tandem. So until we have a general purpose quantum computer, I'm not sweating the whole AI revolution thing. Besides, if they're scary robots, remember all the Boston Dynamics stuff runs on diesel. So just hide out for a couple hours and runs out of gas and building something new, right? So when did this all start? Well, now it's time for our quick history of quantum. This is so interesting to me because there are so many actors in this that don't get credit. Men and women, scientists, material scientists. I'm not going to be able to cover them all in this talk, but I'm going to give you a couple of the highlights. And we're going to start with the 1830s, when Babbage invented the first general purpose computer, and Ada Lovelace basically built the world's first algorithm. And so this kind of started off this computer science field. And if you'll notice, I broke this into 3 areas because quantum computing isn't just computer science. So we got quantum mechanics, computer science, and information theory. And what we moved to 1926 when Schrodinger derived his wave equation, okay? And this was all quantum mechanics. It was an incredibly key point to building off this technology. In 1927, there was a conference called the Savoy Conference. And this is where some of the world's most notable physicists, Schrodinger, Einstein, Heisenberg, all got together. And a lot of work was done there that moved this because they formulated a quantum theory, which started basically this area, this field of research. In 1935, how many of you guys know Schrodinger's cat, right? Everybody. Incredibly morbid thought experience, I think. But for those of you who don't know Schrodinger's cat, it's basically an experiment that we'll talk about in a minute, where we put a cat in a box, put gas in the box, and we don't know if it's alive or dead till we check. So it's a really weird state experiment. But basically, Einstein, Podolsky, Rosen had this paradox questions. They basically came up with this idea of entanglement, this idea of quantum superposition, and we're going to get into that in a little bit. Back to computer science, 1935, Church-Turing, right? The thesis introduced the notion of what it meant to function to a computable component. If you look at that graph, I've tried to illustrate that, although I didn't realize how tiny it would be on the screen. And then we go to 1948. Information theory takes a huge leap forward, right? There's a new theory of communication, a new theory of digital information. Continuing on, 1982. That is a Bloch sphere. And we're going to get into this in detail more, but this is one of the primary differences between the way a computer works in a classical system and the way a computer works in a quantum system. But this is also the marriage of quantum mechanics and computer science. This is where these two start forming and coming together. Moving on, this is the first quantum circuit. And we'll get to this later on as well. But basically, this is a quantum Turing machine, a huge advance. That involved all 3 of these areas of science: quantum mechanics, quantum science, computer science, quantum information. And then, in 1989, annealing came into being, okay? Continuing to move on, 1994, Shor's algorithm. How many of you guys have heard about Shor's algorithm, right? This is the thing that will break encryption. We're going to break that down in a few moments. First quantum logic gate, 1995. Grover's algorithm. Now that was supposed to, when I first drew it, be a needle in a haystack, but it looks more like a match in a whole bunch of other matches. Because I was thinking this presentation was literally going to just on fire and burn. So that's my team is the only people that laughed at that. That's weird. I don't feel like they have that much confidence in me right now. So 1997, KF proposed a topological quantum computation. 1998, back to that quantum circuit gate. It actually becomes a real thing. Oxford demos it on a 2-qubit system. Qubits being the quantum version of bits and the fundamental building block of these computers that we're talking about. Now, getting back to Nishimori, he proved quantum annealing conjecture, and he is a superstar in the space. As one of the things I want to do is give you guys resources. If you're going to Google about somebody, great person to research. Now we start speeding up. 2000, Los Alamos achieved 7 qubits. 2006, Institute for Quantum Computing at MIT achieved 12 qubits. It goes on. D-Wave starts building annealers. In 2011, the D-Wave 1 has 128 qubits. But in 2013, the D-Wave 2 had 512 qubits. Do you see that path, just like those patterns of things picking up, going up and to the right? 2015, D-Wave 2 achieved a 1,152 qubit system. This is super exciting because now we get up to present day almost. In 2007, to show you the pace of advances in this science, IBM achieved 3 things. 1, they broke the 46 qubit simulation barrier that everybody said couldn't be broke. Number 2, they displayed and demoed a 17 qubit quantum computer. And then in the same year, demoed a 50 qubit quantum computer, and they've made a 20 qubit quantum computer available to people over the internet. Okay, their top customers, you have to apply and stuff. So that's a huge advance just in 1 year. Now, Microsoft also released Q#. Visual Studios. So if you haven't got the idea that this stuff is picking up, that this is really taking off, imagine Microsoft betting the farm on quantum and releasing Visual Studio with Q# so that you could program a computer that doesn't even exist on a simulator, because it's just that damn important. 2017, Intel achieved 17 qubits. And then finally, just this year, last week, Google showed that they have a 72-bit quantum chip. So that means we started at around 17 in 2017, and we're not even to the middle of 2018, and now Google has a 72-bit machine. And I believe you'll see IBM and Microsoft in the next couple of months make some pretty big announcements related to this too, and you'll see this even continue further and faster. So what exactly is a quantum computer? Well, before we can do that, have you ever thought about how a computer actually works? Because in the original days, you had to be an electrical engineer to program a computer because you had to understand the voltages. And then you just had to understand the gates. And now a lot of developers don't even know or think about gates. Right now, you do have to be a physicist to program a quantum computer. I hope to one day change that and take us to the gates. But if we break a computer down, we've got circuits and modules and our logic gates, and then we've got our transistors. Now back to that slide on bits are dead and kind of that a little bit of what I think is the FUD in quantum computing. One of the things that is often talked about is that my phone has a processor that has 30 billion transistors in it. And so if we look at this diagram, we think about how a transistor works. If we don't impede the flow, we get a 1. Our little particles float on through. And if we do, we get a 0. This is a basis of computing. But we are getting so small that that may come into question. How small? Well, to put in perspective, that phone example I gave you, 10 nanometers, a virus, 20 to 400 nanometers, right? A nanometer is the length your fingernail grows in about a second. A strand of human DNA is only 2.5 nanometers. So think about that. The size of these transistors, because we already see fabrication for 7 nanometers, we already see fabrication coming for 5, is getting almost equal to the size of a strand of DNA. That's really, really small. To put that into a little better perspective, if a nanometer was a marble, the Earth would only be a meter in diameter, okay? It's quantum apocalypse. The reason is because people are worried about something in quantum mechanics called quantum tunneling. And what that means is that particle we talked about earlier, we can't block it. Things are so small that although we try to block it, it just goes through anyway. So if you are a fearmonger, computing as we know it could break down because we can't create calculations. I don't personally believe that. So with that in mind, what exactly is a quantum computer? Well, again, unlike a standard system where you have a 1 or a 0, in a quantum computer, you have a photon. The photons have spin. And because they have spin, it can be a 1 and or a 0. This is quantum superposition. And because of that, a whole bunch of other stuff changes. For example, we can see how a computer works. Computers work by manipulating data, okay? And we can see them manipulate that data. But in a quantum system, we can't see what it does. We can only measure the result. So this is going to bring about a whole new science of computing, a whole new set of things that we have to learn as developers and as engineers. But to put it in succinct points, you can compare classical to quantum theory in a couple of key points. One, the state of multiple bits is defined in classical theory by the number of individual bits. But in quantum theory, those bits can equal a sum greater than the number of those bits. In classical theory, everything can be copied. We can copy the data, but we can't do that in quantum. We can only copy the results. We can only see what we measure. Now, there's 3 types of quantum computers I want to tell you about. And if you go to Wikipedia and you go look up things up, there's a ton of different quantum languages and different types of quantum computers and everything. These are the 3 things that I think you really need to be concerned with. I think these are the 3 mainstays. You have annealers, okay, which is what D-Wave makes. And you have a circuit gate model. So the difference between those two, an annealer is a great optimization machine, all right? And that's primarily their field. They approximate things. A circuit gate works a little bit like, almost exactly like, how you think a normal computer works. So these are going to be, probably when you see the world's first general purpose computer, it's probably between the two going to be a circuit gate model. Now, there's a third type of quantum computer, the topological quantum computer, which uses topology, which is a form of math. And I put it up there. It's some real black magic shit. I don't think anybody fully understands it. But that's kind of a joke. So if you have a qubit, and you have a bunch of qubits in the system, the reason that topology is important is that you could perhaps have a system that has better fidelity and that has better noise reduction in the system. One of the problems, error correction, in quantum computing is a huge hurdle. There's a lot of startups working, a lot of people working on it. Decoherence sets in on these systems, which we'll talk about in a moment, very, very quickly. But a topological qubit could store multiple parts of data across the multiple qubits and could be incredibly useful to reducing that noise and taking our first real steps to a general purpose quantum computer. Now, we talked about quantum tunneling. Let's talk about quantum superposition. This is the ability for that bit to be a 1 or a 0 or anything in between. And it's constantly in there changing until we measure it. At the point where we measure it, then we can see what it is. This is why when you talk to somebody in quantum computing and they give you a math example, like, oh, we could use Shor's algorithm in factor 15. We know it's 3 times 5. They also throw out like 48% of the time. Because that's kind of how, this is one of the factors that drives that. The other thing is quantum entanglement. So this is an often confused topic, and even when I first started learning all this, it was very confusing. So what you'll often hear misstated is that quantum entanglement means that all of these little atomic particles are entangled, and people will often mistake that you can measure one and know what the other one is. It's actually not true. That's why it says, I know you, and it says, I'm stupid. Because the first qubit can know of the other, and by affecting that, does not know anything about that qubit. So you are not measuring one and seeing the results ever. This is why you can't have communication that's faster than the speed of light. This is why you cannot have a system. You hear often in quantum entanglement, people say, oh, well, if I have a bit of particle over here, no matter the distance with the other particle, then I can instantly measure them. But you have to have classical information in that system, in that transfer, and that slows things back down. So these are all very interesting, but let's talk about the anatomy of a quantum computer. And this is where I'll slow down the pace a little bit. This is what most quantum computers look like. It's a big tube to shield everything environmentally. And inside of that tube is something that looks like the greatest steampunk computer art I have ever seen in my life, because it's all brass. But what you're talking about here is you're talking about a series of cooling systems. So as these rings get smaller, they get cooler. So the cryogenics in it allows us to take the information, put it in the quantum computer, take it all the way down, in IBM's case, to 0.5 millikelvin, and then do the calculation, and then bring it all the way back up. At the bottom of that, in that little bitty tube, there's a processor. That's the quantum computer. Everything else you see is primarily cooling system. And so down in this chip, there's a bunch of different ways to do this. Michelle Simmons and her team in Australia are working on ways to embed them in silicone. There's a variety of different ways, and everybody thinks that their way is the best. There's not a standard necessarily established yet. That doesn't mean that people aren't doing the same thing for how you build these chips. So this isn't ARM and Intel building chips and making them faster and faster. Everybody's kind of in their own game right now. But I believe that we'll see a 100-qubit computer, which when I made the presentation, was not a safe bet. At 72 in March is maybe a safer bet this year. And again, I don't believe in quantum supremacy. You'll see Google talk about quantum supremacy. And this is not to slight Google. I use all their products and love them. But how can a computer be superior if you have to still have another computer attached to it, right? And we need classical computers. Again, this is a marriage of the two technologies, not a distinct point in time where there's no more classical computers and all we use are quantum computers. And as you can see in this diagram, we take the data at room temperature, we cool it down, It goes all the way down cold in space, and we bring it back up and we put it back on the classical system, and we can see the results. You can try this for yourself, and we'll talk about that in a couple of the sections where we talk about some resources. Now, this is where it's going to get weird, because if you look at a quantum calculation, the obvious one to use is a Fourier transform. And I am not a discrete mathematician. I am not super great at math, but I think I can explain this to you in a way that'll make it a little simpler. And that is the death of RSA, everybody's worst fear. So Shor's algorithm, right? That's how we would get to that. So what would we do? Well, we don't need a quantum computer to necessarily do it. We just need access to quantum cloud or some sort of quantum coprocessor. Because what a lot of people don't understand is Shor's algorithm is not just a quantum algorithm. It is an algorithm that uses quantum computing, but the majority of it is actually all classical work. So now the maths. All right, so we want to make sure n is not odd, okay? Because if it is 2 is not a factor, and if it is, that's it. That's the end of the experiment, right? Then we want to check that n is the product of 2 coprimes, all right? Now, the reason this is important is that this is already a fast classical algorithm to do this. This doesn't involve quantum at all. In fact, step 3 doesn't involve quantum at all. I went past step 2, sorry. So you take a random number, check that it's a factor. If it is, again, we're done. Step 4, this is the quantum part of Shor's algorithm, right? This is where we want to find the ordering. This is the key, the heart of what Shor's algorithm really does. There's no classical algorithm that can do this. This can only be done in a quantum system. This is where you find the period of the function of xk mod n. And so it's a non-deterministic quantum magic, because the number of qubits also affects the precision with which we can do this measurement, okay? There's a slide coming up for everybody in a minute, I promise. And then if R is even, all holds true, then we can find the factors. Otherwise, we go back to step 3, right? But again, it's very important to understand that there's only one quantum step in Shor's algorithm, okay? All those other things are classical, and there's already fast algorithms to do those. Now, what happens if we want to factor 15? Okay, 15 is not an even number. Check, we're good. All right, and you might notice, I didn't know if anybody saw that, I had my physicist triple check that 15 isn't even. There was a very big debate on that earlier. Now, 15 is a product of 2 coprimes, so we're good there. And 7 is not a factor of 15, so we'll need that for the next step, because what we'll do is we'll find the order, right? Also, fuck number theory. Am I right? Everybody can agree with me on that right now. And as most of your physics professors told you, the exercise is left to the reader, so you can do this at home. But if we look at this, R is even, right? And GCD for the win, we've got an answer. And what is that answer? Here's a slide for everybody. TLDR, 15 is 3 times 5. So I don't know who went woo, but thank you. Because I don't like those slides at all. But that's the deal with this. This isn't just about, as a developer, as a computer scientist, I'm so excited about this, but I can't go it alone. I need a physicist to explain all the quantum mechanics to me. I need a discrete mathematician or someone good at topology to work through all the math with you. This is going to be something that takes a lot of diversities in thought and experience to create these algorithms, to create useful algorithms. Now, why do we want one? Probably the best question. So here's a couple examples. Michelle Simmons, who is very big in this space, often gives examples of the traveling salesperson. So let's say that we want to optimize the path. We want the shortest distances, and it's very important to understand that we need the shortest distances between 2 points. And we want to send a salesperson to 14 cities. We have a computer that does like 10 to the 9th operations per second. So that's a 10 to the 11th problem. It takes that computer about 1,000 seconds to do that. However, if we increase the number from 14 to 22, it becomes a 10 to the 19th problem, and that takes 1,600 years to process on that same computer, okay? 28 cities, longer than the time of the known universe. So there are problems in computing, and traveling salesman's one that's debated and argued, and people are like, oh, I've solved it this way, solved it that way. But there are real problems that are incredibly hard for classical computers to solve. Now, there are people who will say, what if would I blow your mind if I could tell you that I could build a laptop and build an algorithm that would do that traveling salesperson problem? And there's all kind of different arguments about it. But this is an example that has been thrown out that I think is a very relevant example to give you an idea of how complex some of these problems get, how fast. Again, the key to the traveling salesperson problem is the distance between the 2 points. We're looking for the short. Now, Bob Suter at IBM recently gave an amazing example, a caffeine molecule. So you guys all like caffeine, right? Nobody's had any of that this week. Caffeine molecule has 95 electrons. So let's think about how we would model that in a system. Well, that's 10 to the 48th, right? So lots of zeros. If you think about the atoms of the Earth, it's about 10 to the 49th, 10 to the 50th. Now, you would need a memory proportionate to 1/10 the size of the Earth to represent that accurately. And so a quantum computer could potentially do that, because it is a quantum mechanical system, in about 160 qubits. Remember, Google's at 72. I think 100 happens this year. I wouldn't be shocked if 160 happens. The problem will not be adding additional qubits. The problem will be keeping that noise we talked about down and having high fidelity within the system. So what are we going to use it for? How many of you guys enjoy the South by Southwest traffic? Nobody, everybody's been to every meeting on time, right? Traffic hasn't affected you guys at all. For those of us who live here, it has been an even worse nightmare. But the thing is, how do you solve traffic? Well, D-Wave and Volkswagen recently did a joint venture in where they used a D-Wave quantum annealer to optimize traffic paths. This is super important. If you guys are a big fan of like Elon and self-driving cars and things like that, how are they gonna optimize where they go and how they go in that future where we don't own a car? This is something quantum computing can do very, very well, this optimization problem. Cancer, nobody likes that. But drug discovery is a very tedious, slow, laborious process. A quantum computer could help dramatically in that process. And finally, the one that's close and near to my heart, is global warming, climate change. The issue with climate change is that it can be argued because most of the science can be disproven. Because in a classical system, it is very, very hard to model a quantum system. And so what happens is, a lot of the forecasts we make, all due respect to all my client scientist friends, they prove to not be accurate. And that gives people the ability to say, well, then it's not real, because you can't show me that you said this was gonna happen and then it was gonna happen. Since nature is quantum mechanical, since quantum computers are quantum mechanical, we should be able to build much better models of the climate, much better models of the effects of climate, the effects of things in the oceans, and really, really hit home with this. Now, we don't have the compute power to solve these problems right now. It's not going to be done by a giant supercomputer at a government research facility. It could be done by a quantum computer, and it could be done if that quantum computer is made available to everyone. If all of this complex math and science I'm talking about is actually reduced down to something that developers can use on a practical daily basis. And so there's a lot of people heading in that direction. Now we get to you heading in that direction. How can you get involved? So you don't have to be a physicist to start playing with this. You don't have to know a lot of math. God knows I'm living proof of that. But what you can do is you can go check out some of the free tools, Microsoft's Visual Studio. You can go play around with Q#. They've got some video tutorials. They've got some lessons. You can go do this today. So even though these things are a little far out, there are things you can play with right now at this very moment in time. IBM also has some tools that are available. They have some things you can sign up online and some simulators. You can run some stuff in a command line and go and make it happen. Open source tools are really interesting. My friends at 1QBit have something called the QDK, Quantum Development Kit. You can go talk to them and check that out. IBM has a development kit called the Quiz Kit, which is super cool. And Rigetti has something called Forest. So there is open source that you can go get and play around with this. And there are programs from each of these people to get you onto a quantum computer. Sometimes you have to play. It's still very expensive, so giving away the, hey, everybody can try it is divided up in some weird ways sometimes. But you can go do this. You can definitely run it on a simulator emulator today, this afternoon. You can literally walk out, download some of the free tools, go check out Microsoft or IBM. It's probably the easiest to, and you can run some calculations. And you can kind of get an idea of what it'd work. And you can be really disappointed because then you go and you type in a command line, and here goes your algorithm, and it says, and boom. And you're like, wait, that's it? There's not really a significantly good Hello World example. So another way you can get involved, how many of you guys use Stack Overflow? So, yeah, oh wait, we can clap for Stack Overflow. That's all right. That's awesome. All right, so Stack Overflow today started a new beta of quantumcomputing.stackexchange.com. So this is something that, if you're familiar with Stack Overflow, been in Area 51, they've brought it up. It's now available to everybody if you have a Stack Overflow account. It's a great place to go today and ask questions, or over the next few weeks or whatever. I'm a huge fan, although I also will put things in and people will be like, that's a stupid question. So again, it's still Stack Overflow. But this is a great place to go. See, I now know who all the developers in the room are. So don't be afraid of this stuff. This is not going to break encryption. It's going to bring stronger encryption. This is not going to bring all of these adverse effects or shift the economic model or this or that. Computing's not going to break down anytime soon. Okay? This is something that's going to bring about massive advances in material science, and drug discovery, and safety of airliners through optimization of digital twinning of very complex quantum mechanical systems. Cure diseases, maybe even help us solve climate change. So I am super excited, and I would ask for you to be inspired, not afraid. And so when I first signed up to do this talk, they said, you have to talk for 45 minutes and take 15 minutes of questions. And I decided that each question would take 7 minutes. So I'm leaving 20 minutes for questions. I hope you guys have been putting your questions in Slido. And before we get to that, I'm going to let you take a screenshot of this. We will tweet this out from @StrangeWorks on Twitter. But these are some books that you can use to get started. Aronson's quantum computing book, quantum computer science, #4 is probably where I would start. That's the book UT is using actually to teach their course. And you can go and you can look into these. Now, I had some nerves about coming up and giving this presentation because when we get to the Q&A, I was like, is anybody going to ask a question? Because I did another one in Germany and there were like no questions. People were like, yep, thank God he is off stage. We're done here. But I have copies of my best quantum computing work to date. Quantum Computing for Babies. Now, these copies are for the best questions, hoping that in a moment when they turn the screen over, it's not blank. And I'll say, well, thank you for all of your time. And Quantum Computing for Babies is actually the hardest thing I've done in quantum computing. So I have to tell a little funny story before we get to QA, which is a friend of mine, Sloan Foster, posted Chris Ferry's books. He's got Quantum Optics for Babies, all these quantum books. Posted them on my website, said, you got to buy these for your 2-year-old. And I was like, of course. I mean, that's awesome. And I bought them, and then I took a picture of him because I thought, people that do work like this, they don't ever get thanked. And I sent it to Chris, and I was like, hey, look, it's my kid reading your book. He can't read, and it's Quantum Optics for Babies, but it's super cool to me. And he mailed me back, and we started talking, and we ended up thinking, you know what? Quantum computing needs a baby's book. I swear we were not smoking weed. Because in hindsight, I'm like, wait, quantum computing needs a baby's book? And I told my wife one night, I had a rum and coke, and I said, you need to leave me alone for a couple hours? I go knock out this kid's book. And I sat down with Chris's spreadsheet, and I was like, boom, this is a ball. It can be red or blue. It's a bit of data. And I was like, that's awesome. Took a couple more drinks. 9 weeks later, I was with the editors, and they're like, entanglement has a lot of letters in it, and it's kind of a big word. And we were looking at page 24, and we like to not use more than, say, 3-4 words on each page. And I thought I was going to lose my fucking mind writing this kid's book. But I have copies for the best questions, and now we are going to get to your questions, and hopefully I will be able to answer them. All right, see. What is I just like the way that one's worded, wherever it went. What is the most futuristic, most sci-fi crazy shit that is actually obtainable within the scope of progress we've made now with quantum computing? Zach gets a book. Zach, tweet me at whurley or something, tell me how to get you that book. That is a great question. And so, you know, there's so many things. I think right now we haven't done a lot. This is the Achilles heel of quantum computing that not a lot of people in quantum computing want to talk about. There's not any applications. There's Grover's algorithm, and there's Shor's algorithm, and then there's not a lot else. I mean, there's this thing called the quantum zoo you can go Google where all the potential algorithms are up there, but nobody can really name like the killer app of quantum computing, okay? Now, that's okay. We saw that inflection point. We know we're going from not a lot to like now more interest, now more funding, now more patents, now more tools. So what I would say is, you know, get involved now and build that. I compare it, and my friends in quantum hate this, especially my physicists, but in 2007, Raven Zachary and Chris Messina and a couple of us, Mark and Dom and all these guys got together and we formed iPhone dev camps. And we're like, there'll be apps on the iPhone. And Steve Jobs was like, no, you'll get the apps we build. And then like 3 weeks later, he's like, in the App Store where everybody can build apps. And there was this explosion of apps on the scene, right? And most of you have lived through that and remember that. I think that's where we're at with quantum computing in the next couple of years. I think as we democratize access to this, as it becomes more available, as we build tools that are abstraction layers from the complexity, I think there will be the opportunity to build more and more cool solutions and cool algorithms, and that's where we'll see that mind-blowing sci-fi shit. But until then, it's going to be a little difficult. Will quantum computing enable time travel? If it does, I need to be the first to know so I can come back to March 13th. Actually, no, I don't want to redo the presentation. To the summer when you ask me to give the presentation and be like, you know what, I am really busy, so I don't think I'm going to be able to do that. Can Google already do Bitcoin mining using their 72 qubits platform? No. I don't think they can do anything with that platform now. I think there's a 72 qubit chip, and they will go and figure something out with it. What else do we have here? If I can bring the questions back up. There we go, because there was one that was really interesting. I'm trying to see which one's been uploaded. I'm so old and blind, isn't the fact I have a monitor that has giant letters. I'm like, what does that say? What role does quantum computing play in blockchain? Okay, that's a great question. A lot of people are worried that using a quantum computer, you'd be able to break the underlying encryption of blockchain. I believe quantum computing will one day break some of these forms of encryption we have, even the RSA. But let's think about how these machines work. It's not a computer that runs 24 hours a day, right? We cool everything down and we get the whole system set up, and then we do a calculation on it, and then we have to reset that system. So it's not gonna be this mass, all encryption's broken, everything's done. But again, looking on the positive side, there's already quantum proof, which I think is a horrible branding, blockchain initiatives going on. There's already initiatives being created to create quantum encryption, but I also ask you to use your logic and common sense on this one. If I have a 72 qubit machine, and that 72 qubit machine can break your key, why don't you take the length of your key and make it 6 times as long so that I have to get to like a 400 qubit machine? Security is not a destination, it's a journey. Threat and remediation are tied together continuously. So it's not like, oh, quantum computer, boom, encryption's dead, none of you have privacy. It'll be like, oh, there's some problems, there'll be some solutions, and then we'll repeat over and over, and as we always do in security. So this is a good one. Emily, also tweet me at whurley, because you are gonna get a book. How do you see everyday consumers interacting with quantum computers once they become readily available? So it's not gonna make the cat videos on the internet faster, but let me tell you what it will. And by the way, Emily, I'm not assuming that you like cat videos on the internet. I like cat videos on the internet, so that's why I'm using that. You have to think about this as Google has a big interest in this. Why? Well, if you have a computer, and let's say you have a phone number you're searching for, and you have a list of names, it goes line by line by line really fast, and it finds that. In theory, a quantum computer would only need the square root of the number of entries to find the same thing. So I think Google will have primarily quantum computers doing a lot of some co-processing of data to make your searches more faster, and more accurate. Let's see what else we have. Does quantum computing have the same scaling ability as classical computing? This is somewhat hotly debated because yes, it has scaling, but no, it's not Moore's law. And again, I don't think it's an extension. We're not ending classical computing and starting quantum computing. And so just like you have all of these cool things like, all your GPUs, et cetera, you're going to have this marriage of these systems. And I think it's undetermined as to how much those will scale, how fast those will scale, what will happen with those. Is programming a quantum computer anything like using C, Java, assembly, or whatnot? And that's from Mars, which just have a great name. You are also getting a book. Do you like how much I've got a whole complex system on this book thing? This is a great question. If you're into machine learning and you've been using all those Python libraries and you want to get into quantum computing, what you'll find is there's a lot of Python. So yes, you can use Python is primarily one of the leading things that you can use to get involved with it. And so if you know Python, there are some pretty cool things you can do with like Andrew's QDK kit at one qubit and some of these other kits that are available. Oh, okay, interesting question. What are the best case scenarios for how quantum computing could embrace democracy and civil society? Such a South by question. I believe that technology should be free. I believe that technology should be democratized. I believe that we don't know where the next solution for solving a intractable problem or curing a disease will come from. And so I want to see it out as much as possible. I think, though, that the question really isn't about quantum computing. It's about data. Will data do what you just asked? And if it will, then quantum computers will help us do that faster. But as we saw in the last election, maybe it goes the other way. So that's a really, really good question, but I don't think it's going to be a direct impact on those things. Will financial markets become more efficient with quantum computing use case development? This is very near and dear to my heart because I believe that quantum computing in the very near future, and there's already hedge funds that are messing with this, will become, if you read Michael Lewis's Flash Boys, the new high frequency trading. So back in the day, people were making trades and they found out if you drag a T1 line or whatever straight to the market and you saw the transaction, you could actually beat it to the market and make a trade on it. And it became a big thing, and then eventually things got evened out and regulations, et cetera, et cetera. I do believe that the first financial company to have a general purpose quantum computer, whether it be for things like quantum Monte Carlos or doing trades on the market, will have a strategic advantage for some period of time. Is that delta of time 6 months or 6 years? I have no idea. If you still believe that programming as we know it today will become irrelevant because of quantum power computers, will programmers, I think is what they meant, themselves? Ruben, book for you. That's a great question. And this is where I'm going to go off my own little deep end, which is, given the information sciences, the computer sciences, the quantum mechanics that we've mentioned, I am not convinced that we will program quantum computers. I believe that we will program computers that program quantum computers because of the nature of complexity. And so that doesn't necessarily mean that programmers are gone. It just means they're working on different stuff. It's like, everybody's like, oh, machine language will put programmers out of business. It's like, that's weird, because that's all you guys program now. So I don't think it's going to be the end of any of that. We'll take a couple more questions. Who would you have wrap your book as a read aloud? This is easy. This is one of two people that I met with here at South by this year to talk about quantum computing. It is either Stephen Wolfram, which would be hilarious. Come on. Because it'd be like Christopher Walken reading Goodnight Moon. It would be great. I'm a huge fan of this. In fact, I will publicly ask Stephen to wrap that book. Or it would be Ray Kurzweil. or it would be Wu-Tang Clan, which are actual rap artists. But if I had to pick between Wu-Tang Clan and Stephen Wolfram, I mean, like, they're cool and all, but have you guys listened to Steve talk? I would just like to see his brain slow down enough to read something so simple as quantum computing for babies. It could explode. All right, we'll get a couple more questions. How can business schools help speed the time to mass commercialization? That's a great question. I think schools play a very important function in this, not just in the technology side, but in the business side. And so we made an announcement today, and this is not meant to pimp this, but it's super cool because it is exactly the answer to Tom's question, with CERN. And so there's an effort now to send students who don't have access to the quantum mechanical physics, to the collider, to all the quantum computing stuff, and don't know how to be entrepreneurs, to CERN for 5 weeks during the summer, which will happen this summer, so that they can be taught all of this stuff, have access to everything, and they can also learn entrepreneurship. And so the answer to your question for me is that we want to be able to teach people how to take these sciences and these complex things out of one part of the university and commercialize them in the other. Now, universities have technology commercialization programs, and that's super interesting. And that happens, to be cool, but a lot of those things take a lot of time, they don't work. I think we need some real startup genes injected in those universities, and the business school is probably a really great place to do that. All right. You've worked on so many different types of projects and companies. What motivates you? How do you decide where to focus? What's next? That is not even related to quantum computing. Like, no book for you. But I'll answer it anyway. You told you I was crazy, right? It says like, mind control skateboards, taser drones, quantum computing sounds cool. I think I'm doing that now. You should try being my wife or in my family. And just being like, oh no, I'm not doing that anymore. I have this whole totally new thing I'm doing. I'm just passionate about technology, but I'm specifically passionate about huge leaps in technology. Points in time where we take great advances, right? The iPhone could kind of be looked like that. Go back to the mainframe days, or when IBM was like, hey, 3 computers in the world should do it, we're good. I think quantum computing is this giant shift. As an entrepreneur, I want to ride that wave. As a technologist, I am fascinated by how much stuff I have to learn. I have read more in the last 2 years than I have in my entire life. I put the baby to sleep. Sorry. It's either a good thing or a bad thing. I don't know. All right. We'll take 2 more, and then we'll call it quits. Will quantum computing be available to consumers in the future? If so, how would we be using them? I think we answered that one with the Google question. In an ideal world, here's a great one to end on. Where do you see quantum computing in 50 years? I believe within 50 years, way before 50 years, we're going to have a general purpose quantum computer. And I believe that general purpose quantum computer will enable us to have a true AI. Not the scary, crazy one that goes out on the internet and destroys all the markets and does all that stuff, but something that we can actually use as a tool, a co-processor, if you will, for our brain. And so I think AI is definitely enabled. I also think that in 50 years, quantum computing will have solved some of the optimization problems we have, traffic and flight patterns and things like that. And I also believe that within 50 years, quantum computing will have addressed some of the diseases that right now plague our society. I hope, but I'm not convinced in 50 years, that quantum computing would help address climate change. Because while those others require data and science, that last one requires you. And so I don't think that we can put that all on the quantum computer. So with that, wait, what? I think he gets a good book just for being the only one of you to shout out a question. So I'm gonna repeat his question and correct me if I'm wrong. He said, what about moral questions? Will quantum computing be able to address those? Are you talking about like your self-driving car can kill you and your 2 passengers, or 8 people it's about to run over, like that one? So I don't think quantum computing, again, back to that kind of will it affect society question, and then your question on, will it help us like figure out the moral landscape? This is the role of technology is to provide us with more, better, more accurate data in that scenario, not make those decisions, right? It's technology, not philosophy. So I think if we had that technology and we were able to build an AI and you were to feed it in there, it might give you opinions on that, right? Maybe those are opinions you don't want, right? Maybe that AI is programmed with inherent bias because it's a bunch of like 14-year-old engineers in China or the US or Sweden or wherever, or Switzerland. So no, I don't think that is a role of quantum computing. I don't. But I do think that quantum computing can help us process the massive amounts of data that might lead to discussions, that might lead to some of that stuff. All right, with that, I will let you go. Thank you very much for your time and attention.